Again, welcome to the weekly Forever Green lab meetings. And these meetings are really designed not to be seminars, but designed to give updates and having enough time for discussion and feedback to the research teams. And the group that's presenting today, along with others that are part of the food science program here at the University of Minnesota and beyond. It's exciting to have been able to participate in the development of this relationship between the plant breeding, agronomics, and food science, and connecting these in a unique way that I think is probably unique in the country, in the development of new crops and the markets of these new crops through food science and now PPICS as a new center and its connection to the food industry. It's a really, I think, unique opportunity for graduate students, faculty, and postdocs to be part of this connected set of efforts that are really well connected. So the up-to-date is just part of that overall connectiveness within the program to keep the various components of the team connected with these updates. So with that, I'll turn it over to whoever's in charge today, and would hope that that you would be able to introduce your team and give us an update on the work on Pennycress and Camelina. So welcome.
Say, Don, could I get a question in before I forget, though?
Yes.
Okay, so you guys have ability to change proteins, do gene editing and so on. And I'm interested in flavors, and there's certain characteristics of proteins make them absorb flavors and be a problem. But I don't know anything about plant breeding and genetics. I don't know what power you have to affect the things that are of interest to me. One day I'd like to have some education from you guys.
Well, I think I was just thinking that same thing. For example, we're now doing testing of Kernza, and my neighbors here in my community are actually cooking up Kernza in different ways, and they're finding that there's this background flavor, a sweet flavor and a cinnamon flavor. And so I think that may very well be a test opportunity to determine whether or not the breeders that are working on Kernza could in fact breed for enhanced cinnamon flavor. Yeah. But where is it coming from? Is it in the grain, or is it being produced during the cooking process? So Gary, I'm with you. I think that we need to pull a team together around, as we're starting to move forward around this flavor issue. I think it's a really interesting possibility, because you have this Kernza grain. It's sweet and has a cinnamon flavor, right? So you have one product that you don't have to add anything to get that complex set of flavors. Right?
Yeah. Well, let's put that in the agenda someplace.
Yeah, let's do that. Yeah.
Thank you.
Very good.
Okay, well, with that, I am going to just start us off. Today, we're going to be talking about the Pennycress and Camelina, like Don said. And we have Vaidehi Nakar, who's working with the Camelina protein. Myself, Rachel Mitacek, and I'm working with the Pennycress protein. And then we have Devon working on the flavor side. And then Dr. Till, or Kati, as we might know her from previously, working on the Pennycress oil. So today we're going to cover those topics, just being the functional ingredients from Pennycress and Camelina, the Camelina protein, Pennycress protein. We'll move into talking about the Pennycress oil, and then the flavor research we have going on. So why do we care about the plant proteins? The protein market is rapidly growing, and it's expected to reach $70 billion by 2025, which is just 4 short years away, really 3.5. And with the growing protein market, the plant proteins are taking over a large portion of the market share, as they provide physiological benefits. They can be produced at a competitive price compared to animal source proteins. And then they have a smaller environmental footprint compared to other protein ingredients on the market. Additionally, there is a trend in consumer diets that are leading to more plant-based diets. And there's a lot of soy protein that's being utilized. However, due to concerns of allergenicity, GMOs, and phytoestrogens from consumers, the industry is looking for more alternative sources, and we are looking for more clean label ingredients so we can utilize protein's functional properties in order to get this consumer satisfaction. So a little about Pennycress and Camelina. We've talked about them a lot in this lab meeting. Just as a review, they're an oilseed member of the Brassicaceae family, which is closely related to canola. They have vast environmental benefits as a winter cover crop, as they can reduce soil erosion, nitrate leaching, and they both have short growing seasons, so they can incorporate in a 2-crop system or a double cropping system. Additionally, the seeds contain a lot of oil and protein, which increase interest for 2 ingredients, for food ingredients, which can give us higher crop return value. So protein ingredients play several roles in the food applications. Their functionality imparts abilities such as solubility, gelation, water holding, foaming, and texturizing capabilities. And furthermore, they play a crucial nutritional role in foods. And the nutritional quality of our plant proteins is dictated by their protein digestibility at corrected amino acid score, as well as their amino acid composition. So we know that canola is adequate in the essential amino acids for both children and adults, and both of the protein functionality and nutritional qualities are dictated by the structure and composition of our proteins, being how they're associated, their amino acid sequence, the reactive groups within those amino acids, if they're denatured or aggregated, and then the surface charge and hydrophobicity. And there are intrinsic factors to our proteins, such as the type and ratio of storage proteins that are present within our plant proteins. And then there are also extrinsic factors, such as processing and extraction conditions, which can all affect the functionality in a food system based on the structure and composition. And then subsequently, it could affect the nutritional, as well as qualitative properties being flavor, color, aroma, and just overall quality of the protein. So next, I'm going to hand it to Vaidehi to talk about the processing of the oil seeds.
Yep. Thanks, Rachel. So I would like to start by discussing the processing of these oil seeds to obtain the functional protein ingredients that Rachel just mentioned. So the first step in the production of protein isolates involves separating the oil component from camelina to produce the defatted camelina or pennycress meal. This can be achieved by pressing the seeds with a benchtop hydraulic press to obtain the pressed seed cake, as you can see for camelina, or by using a screw press that we used for pennycress, which is then milled to reduce the particle size. Hexane defatting is also used to get rid of the residual oil that is left after the pressing step. At the end of this process, we get a meal with about 3% fat. So we are investigating 2 different methods, alkaline extraction and salt extraction, which is coupled with membrane filtration. And as we are optimizing these methods, our aim is to achieve a higher yield and purity of the protein. We are also considering the feasibility of scaling up these processes for the industry and producing a functional protein ingredient for food applications. Now, talking about each of these methods, for alkaline solubilization, the proteins are solubilized at alkaline pH, so pH 11 for camelina and 12 for pennycress. And then the proteins are precipitated at acidic pH, so pH 5. The conditions here were optimized based on some preliminary screening with each of these proteins. The precipitated proteins are then neutralized, subjected to dialysis to reduce the salt content within the extract, as the excess salt might impact the protein functionality. And finally, the extract is freeze-dried to obtain the pH extracted protein isolate. For the next method, the salt solubilization, we solubilize the proteins using a low concentration of salt. After this, typically a high concentration of salt was used to precipitate and isolate the solubilized protein. However, considering the impact of the salt on protein functionality, removal of this salt is important and could be expensive. All the necessary washing step may require a lot of water and are unsustainable. Therefore, we are exploring the industry feasible ultrafiltration method, followed by dialysis to remove the salt and other small molecular weight carbohydrates that were soluble in the salt solution, and finally obtain the salt extracted protein isolate. Now talking more about Camelina protein and the results we obtained. But before I dig into my research, I would like to mention that in our lab, Claire Boyle and Pam Ismail had investigated Camelina protein, and that was the first comprehensive study on Camelina protein for food applications. They evaluated the impact of oil pressing conditions, hot press and cold pressing, on the protein yield, purity, structure, and functionality. They also investigated the extraction protocols, alkaline and salt extraction. They found that there was no major impact of oil pressing conditions. However, the salt extraction produced a less denatured and more functional protein concentrate. Moving on, we wanted to further explore the protein extraction conditions to obtain higher yield and purity. We also wanted to improve the color of the protein to enhance its organoleptic properties. Specifically for salt extraction, we wanted to investigate the industry feasible ultrafiltration method that I just mentioned, since a lot of water is used for dialysis to reduce the salt content. And finally, we were interested in screening different Camelina lines or to study the differences in protein functionality. So my first objective is to develop a functional protein ingredient from Camelina, and that would involve investigating effective protein extraction methods and their functional properties to be explored. For my second objective, protein functionality for various food applications such as beverages, emulsions, meat analogs can be explored through evaluation of diverse Camelina lines. So my second objective is to screen the Camelina lines for protein profile, structure, and functionality. My first objective can be divided into 3 steps. In the first step, the defatted meal is produced by expelling the oil out of the seeds using the benchtop hydraulic press, followed by defatting with hexane and milling to reduce the particle size. In the second step, I optimize the 2 extraction methods that we discussed earlier, pH or alkaline extraction and salt extraction coupled with ultrafiltration. Various extraction conditions were screened and optimized for each of the method. Finally, in this third step, each of these protein isolates were evaluated for their structure and functional characteristics. So for structure, we are looking at protein profiling, protein denaturation, the surface properties, and protein secondary structure. Under functionality, we are analyzing the solubility, water holding, and gelation characteristics, emulsion and foaming properties. All these analyses will determine the potential use of Camelina protein in beverages, meat analogs, baked products, and other food applications. Looking at the results for each of the extraction, for alkaline extraction, due to the higher pH and oxidation, the protein extracts are darker in color and may have an undesirable odor. Therefore, a reducing agent, sodium sulfite, was used to mitigate the oxidation. The different levels of sodium sulfite were tested, and it was found that 0.1% sodium sulfite was shown to significantly improve the color, as well as led to an increase in the protein purity and yield. So our optimized pH extraction method produces Camelina protein isolate of 83% purity and with a protein yield of 63%. Now looking at salt extraction, based on the preliminary screening, we decided to test 2 different salt concentrations, 0.5 and 0.75. As you can see in the table, there wasn't a significant difference between protein purity, yield, and ash. So we decided to go with the lower salt content so that we have lesser salt to process at the end. And our optimized extraction methods produces a protein isolate of, again, 83% or 84% and a protein yield of 55%. Now, looking at some of the structural properties, I would like to start by protein profiling. We also analyzed the commercial soy and pea protein along with our camelina isolate to compare their properties with the commercially available proteins. While looking at the protein profile, let's simultaneously also review major proteins in camelina. We have 11S cruciferin, which is a hexameric protein, and it has one acidic and one basic subunit, which is shown by pink and blue spheres. They are linked by disulfide linkages. So you can see on the gel and the non-reducing, we see the monomer around 50 kilodalton, which is then reduced to 30 and 20 kilodalton under reducing conditions. Now looking at 2S napin, it has a short and long subunit, which is linked by two disulfide linkages. Their molecular weight ranges from 12 to 14 kilodalton, which again can be confirmed from the gel. And under reducing condition, they are reduced or lower than 10 kilodalton. And overall, looking at the soy and pea isolates, these isolates have higher molecular weight proteins as compared to camelina, which may further impact the functional properties. Moving on, here we analyze the thermal stability and denaturation state of the proteins using DSC. The presence of endothermic peaks indicates that the proteins are denatured, and absence, like in case of commercial soy and pea protein, indicates that these proteins were already denatured during their processing. Now, looking at the peaks for camelina isolate, we see two peaks from literature values. The ones on the left are cruciferins, and one on the right are the napin proteins. Here, I would just like to draw your attention to the significant differences in the denaturation temperature, as well as enthalpy for cruciferin between the two isolates. This could be due to the severe alkaline conditions in pH extraction that may result in protein denaturation. Moving on to the surface properties. So we measure surface charge and surface hydrophobicity. The balance of surface charge and hydrophobicity affects how the protein will interact with its surrounding, thus impacting its functional behavior like solubility, gelation, and emulsification. The pH extracted camelina protein showed higher surface charge than the commercial samples, whereas the salt extracted had lower due to the high amount of salt in the isolate that may shield the charges on the surface. And as compared to commercial reference protein, both pH and salt camelina isolate had lower surface hydrophobicity, showing potential for better functional properties. So now let's look at some of the functional properties. So here, the protein solubility is often considered the most important functional property, as it is a prerequisite for the majority of other functional properties. Protein solubility was tested at pH 7 and 3.4 at 5% protein to determine its use in protein beverages. And it was also tested under non-heated and heated conditions to see how thermal processing will affect the solubility. I'm happy to report that the salt camelina isolate had highest solubility at pH, at acidic pH, indicating its potential use in acidic beverages. Now looking at the next functional property, gelation. So we prepared the protein gels and measured their strength using texture analyzer. The salt extracted camelina protein did not set at the conditions that we tested, so we are investigating more on that. The commercial and soy protein and the pH extracted were tested at 15% protein, whereas the commercial pea protein was tested at 20%. The pH extractor showed significantly lower gel strength as compared to the commercial ones, which could be due to the lower molecular weight of camelina as compared to the reference protein as we saw in the protein profile. Since proteins with higher molecular weight are found to form better protein networks and stronger gels. For emulsification capacity, proteins should have a good balance of hydrophobic and hydrophilic residues to interact with both oil and aqueous phase. And both pH and salt camelina protein isolate, shown by the yellow and the green bars, had significantly higher emulsification capacity as compared to the reference proteins. So they have a better balance of hydrophobic and hydrophilic residues. Moving on to my second objective quickly. For my second objective, we screened 40 diverse camelina lines for their protein profile and selected 4 lines for scale up in the greenhouse to produce enough seeds needed to extract and characterize their protein. One of them was spring line and the other 3 were winter lines. Due to time constraints and technical issues at the greenhouse, we were only able to obtain enough quantity of the spring line to extract the protein and get the spring line protein isolate. So moving on, we'll use the optimized conditions for these protein extraction methods and get the isolates and then look at their structural and functional characteristics. And now on the next slide, I screened the 40 different lines that had differences in growth habits and origins that I collected from Ratan Chopra from Dr. Mark's lab. I used a method developed by Krishan Rai to screen the 40 different lines on STS-based gel to evaluate the differences in protein profile. These are the shortlisted 10 lines that showed some differences. The black box shows the Joel line that was used in my first objective, and the other 4 highlighted lines in red showed some differences. As you can see in lane 1 and 2, there were differences in the intensities of the bands around 20 and 25 kilodalton. And then between lane 3 and 4, we observe a difference in the band at 15 kilodalton. We also see quantitative differences in their protein content. So once we obtain the protein isolates, we would be analyzing the structural and functional characteristics. So that's my next step, and you can anticipate that data in the next update. With that, oh yeah, some key takeaways. So we saw that Camelina protein isolates can be efficiently produced using industry feasible methods. And the Camelina isolate showed comparable and better functionalities than the commercially available soy and pea protein. And finally, characterization of Camelina lines, and with the significant differences that we saw, they will feed into the breeding program and help develop Camelina for food use. Okay.
So now I'm going to take it over and talk about my pennycress protein research. Our 2 main objectives, number 1 was to optimize the protein extraction conditions and maximize the yield and purity, and then characterize the influence of the extraction conditions and scale up within the pilot plant on protein structural and functional attributes. And then our second objective is to determine the differences in structural and functional characteristics of pennycress protein from the wild type between the different mutant lines. For today, I'm only going to be discussing my first objective just for the sake of time. We have a lot to get through, but I will be sharing the mutant lines in the next update. So our experimental design is very similar to what Vaidehi had talked about with her first objective for Camelina protein. And our step 1 is the production of the defatted pennycress meal, where the wild type seeds were defatted and milled in the same manner. And then the defatted pennycress meal was subjected to the second step, being the protein extraction, optimization, and production, where we optimize the different protein extraction methods. The first one being the pH extracted protein, or PCP-pH. The pH extracted protein with 0.1% sodium sulfite protein being PCP-PHSS. And then the salt extracted protein, which I'll refer to as PCP salts. From there, when we determined our structural and functional attributes, we scaled up that extraction in the pilot plant to give us a scaled up protein isolate. So this will be referred to as PCP scaled up salt, or SU salt. And from there, all of these, along with our reference proteins being commercial and native soy protein isolate, were subjected to the same structural and functional characteristics that Vaidehi had previously talked about. So looking at the protein extraction optimization for the pH extraction, or alkaline solubilization and acid precipitation, on the left side of the table, we are looking at the extraction conditions. And then on the right side of the table under PCP, the protein purity and yield, are looking at the protein isolate. And then we have the spent pellet to help us measure our extraction efficiencies from what is being discarded within our protein extractions. So under the extraction conditions, the first lane is a degumming step where we solubilize the pellet, or the defatted meal, in 2.5% solids. And then we centrifuge it and take the supernatant, and then we precipitate the proteins out of the supernatant to separate the proteins from soluble gums. And then we add that protein fraction back to the protein isolation. And this is to help get rid of some of those gums just for a higher purity. And then we're looking at the number of solubilizations. So we either solubilize it once or twice at alkaline conditions. And then we're looking at time, pH, and then the inclusion of sodium sulfite. And on this first slide, we're not going to be looking at the sodium sulfite inclusion quite yet. But what I wanted to point out with the first 4 extractions here, we optimized the differences between 1 and 2 solubilizations, and then both of those solubilizations being either 1 or 2 hours each, all at pH 12. And what we found was that the 2 solubilizations for 1 hour each on this third line here gave us the best protein yield and purity. So then moving forward, we wanted to test the differences in the differences between degumming and no degumming. So from this 4th extraction down to the last one here on this table, we saw that getting rid of that degumming step increased our protein yield quite a bit. And we went forward then without doing the degumming step and just looking at the differences in pH, which is here at the last 3 extractions. And we could see that with decreases in pH from 12 to 11 to 10 decreased our protein yield and somewhat increased our purity. However, with the hit to yield, we kept our extractions at pH 12, which is quite alkaline. So our optimized conditions for this extraction method was no degumming with 2 solubilizations for 1 hour each at pH 12. And then we started to look at the color. So this gave us a really brown protein extraction that was quite smelly and oxidized. Here on the next slide, we're looking at the differences between a native SPI and then the salt extracted pennycress protein, and then the alkaline extracted pennycress protein. And we can see how dark that is. So we worked with the inclusion of sodium sulfite as a reducing reagent at 0.1, 0.2, and 0.4%. And what we saw was changes within the color. However, when looking over at the SDS page, we can see under non-reducing conditions that there is more streaking in each of the sodium sulfite included ones, as well as there is a loss of our cruciferin bands, which indicated to us that we were aggregating our cruciferin proteins, which could be poor for functionality. So what we ended up going with was utilizing the 0.1% sodium sulfite, and it played in with another reason that we are going to look at on this next slide. So looking at the extraction optimization, the last 4 extraction methods on the bottom is all the same for all of the conditions, except for we have no sodium sulfite, 0.1, 0.2, and 0.4. And what we saw was that with the increases in sodium sulfite content, we decreased our protein yield, which could also confirm that we were getting aggregates of our proteins that were not being extracted. So we, moving forward, had our 2 pH optimized extracts being the same conditions with and without sodium sulfite. So then looking at our salt solubilization or our salt extraction method of pH, we are looking at the same table setup. However, we have different conditions being the molarity of salt used, the number of solubilizations, the pH, and then if we utilize dialysis after the ultrafiltration or not. And so looking at the first extraction compared to the second one, we found that utilizing dialysis decreased the amount of salt in there, increasing our protein purity, and we utilized dialysis for the rest of the extraction conditions. And additionally, we utilized 2 solubilizations as opposed to 1 solubilization to get more of those proteins within our supernatants to ultrafilter. And then next we looked at the differences of solubilizing those salt-soluble proteins at the natural pH being 6.3 or adjusting to 7 and 8. And what we found was that although there were increases in protein purity, there were decreases in yield. And then ultimately we went with the natural pH and tested the differences at the bottom two with the 0.75 and the 1 molar, and found that although there were slight increases in protein yield, the amount of salt that needed to be removed with the processing decreased. It outweighed the effect of the higher yield, and so we stuck with the 0.5 molar. Going into our structural differences, this is our protein profiling, our SDS page, and Vaidehi did a really good job of setting this up for us. So we can see that under the non-reducing conditions, the commercial SPI and the native SPI both contain a higher ratio of high molecular weight proteins compared to all of the Pennycress samples. And we can additionally observe that both of the salt extracted proteins are less aggregated compared to the pH extracted proteins. And the benchtop salt extracted protein was less aggregated than the scaled up salt extracted protein, as seen by streaking differences in the lanes. And then additionally, we could see that the salt extracted proteins both had higher molecular weight proteins compared to the alkaline or pH extracted proteins by the increases in the band intensity at 50 kilodaltons. And this is likely due to the salt soluble nature of the cruciferin proteins that were not utilized within that high alkalinity. And also referring to that, we can see that under the pH extracted conditions in the reducing gels, we have an increase in these band intensities of the glutellin type polypeptides, and those are highly alkaline soluble. So utilizing those alkaline conditions increase their presence within the alkaline extracted proteins. Now looking at the temperature and degree of denaturation, Vaidehi again gave us a really good setup. And on the right, we are looking at just the differences in enthalpy between a native SPI, the benchtop salt extracted protein, the scaled up salt extracted protein, and then the pH and the PHSS, or pH with sodium sulfite. And we can see with decreases in, or a more straight line, that indicates less enthalpy or more denaturation. So we can see that under the denaturation for cruciferin, the salt extracted benchtop had the highest enthalpy or the least amount of denaturation, followed by the scaled up salt extracted protein in the pilot plant, which can be contributed to pasteurization and homogenization that was necessary within the pilot plant to produce these proteins. And then we had almost complete denaturation of our cruciferin proteins within the pH, and then the pH with sodium sulfite extracted proteins. Moving on to the surface properties with hydrophobicity and charge, we expected that the pH proteins actually would have a more denatured or more hydrophobic interaction, because we saw from the DSC or the denaturation that they were highly denatured. So we would expect that the globular proteins of cruciferin would be denatured, exposing more of those hydrophobic groups and then decreasing the charge. However, what we saw was something that Vaidehi also had talked about within her research, was that the salt extracted proteins may have had higher residual salts in them, shielding some of the protein charges and decreasing the protein or the surface charge of these proteins. And then looking at the surface hydrophobicity, we confirmed that our salt extracted protein on the benchtop, being less denatured, had a lower amount of surface hydrophobicity, then followed by the salt, and ultimately the highest amount of hydrophobicity was our most denatured proteins, being the pH extracted proteins. And so when we look at the high hydrophobicity and the low surface charge of our proteins, that's not really great for protein solubility to be incorporated within a beverage system. So we measured our protein solubility at the same conditions as Vaidehi did for the camelina protein under 2 different pHs, and then under non-heated and heated conditions. And ultimately, we confirmed that the salt extracted protein on the benchtop had the highest amount of solubility, even surpassing the native SPI under non-heated conditions at pH 3.4, which would make it suitable for an acidic beverage, and then followed by the scaled up or the pilot plant scale salt extracted protein. And then what we see under pH 7 is that our salt extracted proteins decrease a little bit in their solubility compared to the soy protein isolate. And then the pH extracted proteins are very low in solubility. And there's a couple of reasons for this, being that the basic nature of the proteins in pennycress, it's closer at 7 to its isoelectric precipitation point than it is at 3.4. And therefore, we're going to have a lower solubility as there's less charge on those proteins. So then moving forward, we are looking at the gelation and water holding capacity of each of our extracts. And again, not surprisingly, the native soy protein isolate, like Vaidehi had talked about, has a higher molecular weight, and therefore it can better undergo protein-protein interactions to have a higher gel strength. And then we had the highest gel strength with our scaled up extracted salt proteins compared to the benchtop. And some of the reasons that we can talk about with that was the higher hydrophobicity that we had seen with the pilot plant salt extracted proteins, to more expose some of those hydrophobic groups of the globular protein structure and increase those protein-protein interactions. And then again, with our pH extraction, we have very low gelation properties. And again, these can all be attributed to the molecular weight and denaturation of the proteins. Then looking at the water holding capacity on the right side, we see, again, not surprisingly, a low water holding capacity for our salt extracted proteins. And the reason that we say unsurprisingly is that the charge of these proteins under the zeta sizer was low, probably because of the salt inclusion of the residual salt shielding some of the protein water interactions. And lastly, we looked at the emulsification capacity, and we can see that the emulsification capacity of the salt extracted proteins on bench and scaled up were increased compared to all of the other samples, which indicates the more intact globular structures and low molecular weight of the salt extracted isolates were better able to interact at the interface of the emulsion to give us a higher emulsion capacity. So in conclusion, we can see that the salt extraction produced superior isolates compared to the alkaline pH extraction due to the higher purity. There was increased solubility and higher emulsification capacity, as well as increased gelling capabilities. And all of this can be due to the structural nature, less aggregation and less denaturation under the extraction conditions. And then we saw that the scaled up salt extraction demonstrated commercial feasibility of pennycress protein production for the food industry. And we saw that with that feasibility and adding those extra processing parameters such as pasteurization and homogenization, we had an increased surface hydrophobicity that gave us a higher gel strength and water holding capacity than the benchtop extracted. And additionally, it did not decrease any of our functionalities because it gave us a very comparable solubility and emulsification capacity. So overall, pennycress protein has high probability and potential to incorporate within a food system and replace current market-leading plant proteins. However, with the low molecular weight proteins inhibiting some of the gelation capabilities, we are hoping to improve some of those with either the mutant lines or some other targeted modifications of the proteins. So our future and ongoing work, currently we are characterizing the differences in protein structure and functionality between the mutant lines. We are currently working with the FAE1 or the zero uracil acid pennycress line. And then in the future, we are looking to investigate structural modification techniques to polymerize the pennycress proteins and then target the functionalization for an increased gel strength, which will help pennycress incorporate into other food applications, such as meat analogs or, other kinds of food applications. So with that, I'm going to pass it off to Dr. Till for the pennycress oil.
Thank you, Rachel. I'm still Kati. That has not changed. So pennycress is an oil seed, and from my understanding, two of the breeding goals in the recent years have been to develop a strain with reduced erucic acid, and that has been successful. And then another objective was reduced glucosinolates, right? And so since Rachel was extracting or pressing that pennycress oil for her work anyway, I thought it would be interesting to analyze that oil a little further. I did a really small study, but I hope it's yielding useful data, because I thought whoever is gonna work with pennycress oil will likely wanna know what products they can use it in and how long it is stable. And so my work addresses that second question. I looked at the storage stability of pennycress oil. And when it comes to oils in general, over storage, they can undergo hydrolytic and oxidative rancidity, and that's summarized in the slides here. So most of the fatty acids are part of triazyl glycerols in an intact plant oil. However, they can get hydrolyzed. And so one of the parameters that's often used to characterize oils measures free fatty acids. So that's one of the things I tested. However, I would say of major importance would be the changes induced via lipid oxidation. And that is a reaction cascade that occurs basically in oils by itself. And two commonly used parameters to describe oils would be hydroperoxide, or the peroxide value, which quantifies hydroperoxides, the first oxidation products that are stable enough to be isolated and quantified. And however, they are not stable for too long. They tend to decompose. And many of the products are carbonyl compounds. And so one test that assesses secondary lipid oxidation would be the para-anisidine value. And so that's what my study focused on. I performed an accelerated shelf life test. Basically, that is done to save time. You subject the oil to slightly elevated temperatures and then use the data you get to extrapolate to room temperature. And on the next slide, I'm showing you the peroxide value for wild type pennycress oil versus the mutant. And I just realized that I'm not even sure how to pronounce it. I think in my head, I always called it fael. Maybe someone later can tell me if that's actually true or not. And so what you can see from this graph on the left is that, interestingly enough, the wild type started out being more oxidized already, and then picked up even faster than the mutant line, fael. And you can model oxidation reactions in oils, and quite frequently they follow a so-called apparent first order. That's because oxygen, or the addition of oxygen, is the rate limiting step. However, the fit was actually not as good. You can see that from the coefficient of determination for the turquoise line for the fael pennycress, likely because it was still in the induction period. And on the right, the figure shows the percent free fatty acids. In both cases, they were pretty low. However, the wild type again had higher values. On the next slide, here are the para-anisidine values. So again, that's secondary lipid oxidation, and it basically just reflects the data from the previous slide, with the wild type already starting out more oxidized and then also oxidizing faster than the fael oil. I know that the oils were kept frozen as soon as they had been pressed. I don't really know much about the history of the oils and if one of the seed types was maybe stored differently, as intact seeds, or if there's anything else that caused the wild type to be so much more susceptible to rancidity, because honestly, I was a little surprised seeing the data considering the fatty acid profiles. I have not completed vitamin E analysis yet, but I started, and I could see that the tocopherol profile, and that's an important antioxidant in oils, seems a bit more, the tocopherol contents seem to be higher and the profile seems to be a little different in the fael. However, I started this research about a year ago, and sorry, there's background noise. Someone's wheeling carts. I hope it's not too distracting. So I started the research about a year ago, and I literally had samples in the incubators when our university shut down due to COVID. The problem with monitoring a chain reaction is that once you've induced the reaction, you can't just take samples out and then the process has stopped. So I actually lost some of the oil. I could only test storage at 2 temperatures, 35 and 45 degrees C, for those samples. But then a few months ago, Connie and David helped me to obtain more oil of the fael type. And on the next slide, I'm showing you the data I have for that. Just peroxide value. I have more, but basically it tells the story already. So I was able to conduct the study at 3 temperatures with the intention to generate a shelf life plot. And that is shown on the next slide. Thank you. So a shelf life plot denotes the end of shelf life versus storage temperature. As I mentioned, I performed an accelerated shelf life study. So I stored at 30, 40, and 50 degrees Celsius. And then these exponential lines that you saw on the previous slide, they basically give you the rate constants of the reactions. And you can use the line equations to calculate the end of shelf life, which for an unrefined oil could be taken as a peroxide value of 10. Refined oils typically shouldn't go up that much. For them, you would choose a peroxide value of 5, but 10 is typical for unrefined oils. So you can calculate when that is reached at a certain temperature, and then use the line equation that you get from the shelf life plot, which is a semi-logarithmic plot, to extrapolate the shelf life to room temperature. And if you do that, it comes out as being stable for about 110 to 130 days if protected from light. So my study was conducted in the dark. And I also made an Arrhenius plot, and that's basically based on the same data. These 2 plots are related. And from that, which plots the rate constant versus the temperature, you can obtain the activation energy of the reaction. And the value that I obtained through that is in the range of what's been found for other oils, higher than flaxseed oil, which would make sense because flaxseed oil is a very unsaturated oil, so it doesn't take that much to start oxidizing it. It's similar to olive and sunflower oil, but lower than a refined soybean oil, which again would make sense because refined oils are more stable. I would like to point out that these are estimations. I only conducted storage at 3 temperatures, and ideally would have done it for would have included another temperature because fitting a line to 3 data points leads to a certain error. However, the fit was actually pretty decent, and the data are in the range of what's been reported for other oils. So that is it from my part, and now we will learn about the flavor.
All right, I will finish up with the flavor work here. We had 2 objectives. One of them was more so for the flavor lab here, where we wanted to optimize the purge and trap aroma collection method for us. There's a lot of ways to collect aroma, and they have goods and bads related to them. The good parts about this purge and trap method is it's not going to use any solvents. It's very reproducible. There's a lot of polymer that actually collects the volatile compounds, so we can collect a range of them and they're not out competing each other. So we can get a representative sample of the aroma of these crops. The second objective here is that we want to take the seeds, the defatted meal, and the protein extracts and look at the aroma compounds over time to see which flavors are produced with the extraction methods and which ones are lost, to see if one of the extracts is a better method for reducing some of the harsher, undesirable aroma compounds. So here we have our samples, and on the right, the top right, this is the setup for how we're actually purging the samples. We put the samples in water, and the nitrogen gas is going to pass through the water and the samples and hopefully collect the volatile compounds and bring them up to the trap on top. So the actual material that's collecting the volatile compounds isn't in contact with the sample, which is helpful for a couple of reasons. If there's a lot of oil in the samples, using other materials will push off the volatile compounds, and then you're only collecting the oil. So the purge and trap method is helpful here because it's only going to be in contact with the volatile compounds. It could collect a lot of them and allows the water to pass through, so we can desorb it into a GC unit with ease. When we're absorbing it to a GC unit, we're having it go to mass spec as well, and we're also going to hook it up to an olfactometry unit so we can have panelists actually smell the odors. And that's helpful because then we can see which odors are going to be stronger and influence the overall flavor of the compounds. And the mass spec is going to help identify the compounds a lot more, with the GC results also helping that and splitting up the compounds as well. So here, looking at the Camelina products, we've started with the seed. We haven't gone to the protein extracts yet, but sort of the key aroma compounds on the right there, they're identified based off the panelists, what they reported as strong or overwhelming odors right now. Further analysis would involve diluting them to actually figure out which of these compounds are going to be the most influential in the overall flavor. But for Camelina, we're seeing a lot of products, aldehydes, alcohols, and ketones that would be related more to oxidation of the oil being left over in those. There's a lot of woody, a little bit of pungent smell that might be more characteristic of pennycress. But right now we're getting a lot of woody, earthy, and a little bit of green aroma coming from the Camelina. That's not overwhelming in those compounds, but a lot of these compounds will have low odor thresholds. So in order to make them disappear with extraction methods will be a little bit harder, because you only need a little bit of it to actually come out as a strong odor. Moving on. So for pennycress samples here on the left, we have the actual seed. And on the right, we have the defatted meal, which is going to be at one point in the extraction method. So on the left, we can see that some of the largest and most influential peaks in the pennycress seed are the isothiocyanates. Those compounds are related to mustard. They're very harsh and pungent, a little bit garlicky, but they're going to be overwhelming and last a while and be some of the most influential odorants in pennycress seed. In the defatted meal, they're still present, but we lose some of the other garlic compounds that's showing up in the right half of the chromatogram here. Those are the sulfides that are produced, and we're losing them. But then the problem with the defatted meal is within the first 8 minutes, we're getting a lot of oxidative products that are gonna be adding new flavors. Some of those green and woody flavors that we were looking at in the camelina seed, those are actually gonna increase in the defatted meal. Next slide here, we have comparing a salt extract back to the pennycress seed. So in blue, we can see the seeds. We have a lot of the isothiocyanates and a lot of those higher retention sulfur compounds. But with the salt extract in black there, we can see that we're losing a large majority of those compounds. Some of those sulfides not even showing up in the chromatogram using the MS ion peaks at all. The compounds that did increase though with the salt extracts are some of the oxidative compounds like the aldehydes and nitriles. The nitriles are coming from a byproduct of some enzymatic reactions, but most of the compounds are from the oxidative reactions. Those are going to become the most predominant and influential flavors of the salt extract compared to some of the isothiocyanates and sulfides that started with the seed. And the next slide here, we're looking at the salt extract of the pennycress versus the pH extract. Salt extract there is in blue and the pH extract is in black there. We can see that major differences between them are the pH extract still has large concentration of sulfide compounds, some of the most influential odors in the pH extract. That could be further reduced with the drying though. The salt extract was freeze dried further, so there is potential for that. But otherwise, the key odorants for both the extracts right now that were present in both to varying degrees. None of them overwhelming though compared to the scene. We're getting a lot of those oxidative products again, a lot of aldehydes there that are going to give a woody and green aroma, and those are going to be more of the influential odorants for the pennycress isolates right now. Next, we are looking at the reactions, how these compounds are actually in there. For the isothiocyanates, that's going to be the main compounds produced by the Synegrin reactions. Those are going to be very key for them. And some of the byproducts of that reaction also produces those nitriles that will give more of a green and woody aroma to them. But the isothiocyanates and cyanides are going to be overwhelmingly mustard, garlic, and pungent. For camelina and pennycress, we see a lot of fatty acid oxidation that leads to aldehydes and alcohols. Those are going to be have very low odor thresholds, which means just a little bit of them are going to be very influential on the flavor, which we saw in the camelina and the pennycress extracts. Anywhere from hexanol to nonanol, we're seeing a lot of compounds go through different reactions to produce different types of odors that all kind of vary around this green, woody, rancid, and pungent odor profile. Some of the other reactions that are present mostly in pennycress on the next slide here. Oh, sorry. So the reactions here on the left, these are going to be more associated with the garlic and onion aromas, where it produces a lot of sulfide compounds, and the mercaptan, where the mercaptan is still present in kind of high concentrations in the salt and pH extract still, and this is going to give more of the characteristic actual seed, pennycress seed aroma that's left over, as opposed to favoring the oxidative products that we talked about before. So some of these sulfide compounds are still present in the extracts, which give it that garlic, slightly pungent aroma. So overall, the pennycress, we see it starts with high concentrations of isothiocyanates, nitriles, and sulfides, which gives it kind of that overwhelming aroma that we'd mostly like to get rid of, as opposed to Camelina aroma is not going to be as concentrated in these compounds, so they're not going to be as influential, and they're going to allow some of those other oxidative products to be more influential in its aroma, but overall not as intense. The preliminary Camelina products are mostly related to the oxidative products and pyrazines. This will produce that woody, earthy, almost bean like aroma, and not as harsh like horseradish or garlic that we saw in the Pennycress samples. And some of the goods of this are that the sulfur compounds that we saw reduced over time. They could be lost during processing just because they're volatile, but also because they readily react with the proteins in the sample. So they will become not as volatile, and potentially they're not going to show up in the purge and trap method or the actual aroma profile of someone consuming these. So some of these sulfur compounds do disappear, and we want them to disappear, and the high proteins in the extracts help get rid of the aroma a little bit. I think that finishes up the flavor work, and we could move on to questions here.
I wanted to just jump in because Ratan had asked a question in the chat. Do I have some thoughts on which proteins in pennycress will need to be enhanced or reduced for increasing the gelling properties? And I wanted to say that the main storage proteins in pennycress they're the same as camelina. It's cruciferin and napin. And our napins are albumin type proteins, which are highly not functional, whereas we would like to see a higher ratio of the cruciferins within the extracts or the seeds in order to have a higher functionality.
So you're saying that we need to kind of enhance the amount of cruciferins that is have more cruciferin than we already have in pennycress.
Yeah.
Okay. Because I mean, so
you want a higher ratio of high molecular weight proteins compared to the low molecular weight proteins.
Yeah, okay. A follow-up question I have on that, like, you know, your gel look really great in terms of, like, you can clearly see napins in pennycress, but the protocol that we've used in the lab, we just use different pH, but we can never see that level of napins in pennycress protein. So I'm wondering, like, if there was somehow, like, if we found pennycress lines, whether they had reduced napins, and that would help us change the ratio. Would that help with the gelling properties?
Yes, I believe that would help because you would have that higher ratio, so a higher inclusion of the cruciferin type proteins that we're looking at.
Okay.
I think as far as your gel going, not being able to see the napins, so we extracted the protein and had the isolates, which is what we ran the gel on, as opposed to doing it from the seeds. You would have a lot more streaking and interference of the other compounds in there that would not allow you to see the napin at the bottom.
Okay. And what you're also suggesting to us is we definitely don't want to reduce any cruciferins in pennycress if you want to maintain the gelling properties. Instead, reduce napins if possible. Right? I'm just reiterating what you told me.
You want
to decrease napins, but not cruciferins. Okay. Yep. Yeah, because, like, we've had some lines where we have reduced cruciferins, but that's not a good approach, looks like, on what you're telling today. Okay.
For food applications, yeah.
Okay. Sounds good. Thank you.
Devon, this is Don. Will we ever be able to clean up the flavor issue to be able to move pennycress into the food system? What happened when they moved rapeseed into canola? Were they facing the same flavor issues early on in the development of canola?
I don't know the canola work specifically, but I know our lab working with pea protein right now that we kind of see some of those beanie oxidative products are always going to be a little bit left over. Some of that sulfur compounds, I think, will come out through processing and become less and less influential. But some of those alcohols, ketones, aldehydes, because they have such a low threshold, they're really hard to get those odors completely out of these protein isolates, I think. And that's kind of normal between some of the plant proteins right now. But in terms of what steps are actually used in industry to remove those aromas, I don't know exactly what they're doing after extraction, if they're doing extra steps to do that.
But in terms, is there another way of looking at it? Are some of these flavors that are in that are coming from the pennycress, is there value to any of those flavors in food products, right? Rather than making it really bland, are there opportunities to incorporate some of those flavors into food products?
How about mustards and garlics and savory products? How's that? You know, one thing we're learning, Don, is we're learning a lot about how proteins do bind flavor compounds. And the more we understand about how they bind them, the more we understand how they release them so they're lost during the process. So, you know, we're kind of chipping away at that.
Yeah.
Yeah, I think it really depends on the use too, because if you're looking at how protein products are used in beverages, you're kind of hoping they're not going to influence the flavor at all, because you're adding other flavor compounds to a lot of these high protein products. And in terms of the flavor compounds right now associated with these, they're not going to be kind of like some of the more dessert fruity products. Someone asked about meat analogs, and some of these compounds are actually kind of associated with meats in general, more savory notes, some of the oxidative
that's what I was thinking in terms
of
those types of products, whether they would have a fit in some of these emerging imitation meat products and the like, right?
But for a meat product, you probably really want some gelling. If you want to use it in a meat analog, you probably need some of that gelling capability, I would guess. And Ron, your question was about canola. I mean, canola protein is not a main ingredient in the market yet, from what I know. And in the canola oil, I guess the deodorization that it would likely go through would remove a lot of the flavors.
Yeah, right.
And the oil doesn't smell that bad. I think the flavor is mostly in the protein or in the pressed cake.
Well, that'll fit very well on a label. It doesn't smell that bad.
Maybe not. No, but I was actually really interested in the oil, and I expected a lot more flavor in the oil. Okay, I'll use the word, and it was really not too bad. It's much better than I expected. Let's put it that way.
That's the line you should go for. Much better than expected.
Well, I like Don's comments. I had to use it.
Well, the exciting part, as you guys all know, is this relationship between this work and the breeders and working both ends, right? In terms of the processing end and the development of new lines that have certain composition in them. And so for me, that is the really exciting opportunity for us for the future, right?
Yeah. So except the flavor, and I see the study compare the protein contents and the stability, etc. Is there any study that try to figure out what Camelina pennycress has this nutrient components or compounds, etc., that soybean or pea doesn't have, and then the Camelina pennycress can provide that to the breeding purpose, we can specifically breeding that fael. Is there any study like that?
I mean, the only thing that we have done so far is looked at amino acid profiles for Pennycress for different lines. And what we have noticed is so far, the amino acid profile is very similar to canola, and there are certain amino acids similar to soybean. We haven't really dug into it. That's very recent development. But what I can tell you is there's definitely some amino acids can be enhanced to have a soybean-like protein or soybean-like meal.
Yeah, the the argument points is you want to deploy those alternative protein with oil, and then farmers will say, how will that be better than soybean? How much more we can make money if we plant Camelina or Pennycress? That is a question for alfalfa too. Also, that's why I'm asking that question.
Yeah, and definitely. I mean, this protein side or the food application for these oil seeds is really like which direction you want to go, because there's a lot of applications. Like just Rachel, like how she mentioned, like we need better gelling properties, and how is that going to affect the amino acid composition? We don't know. Like the moment we start increasing cruciferins, like we got rid of cruciferins in one of our lines, we saw some effect on amino acid composition. But if we start increasing, do we enhance certain amino acid, or do we have that flux towards some amino acid that is not desirable? All of that becomes it becomes a long-term goal, I would say.
Yeah.
But are you, sorry.
Go ahead.
Are you actually, I mean, I thought it was supposed to work in rotation. Are you suggesting that whoever grows it gets rid of soybeans, or grows it in addition?
It would be grown in as a relay or a double crop in the same year with soy.
And before I forget, how do you say it? FAE1 or FAE?
You said it right, FAE1. Yeah. It's called, it's a fatty acid
elongation, yeah.
One. It's a gene that was identified in Arabidopsis, and they call it FAE1.
You know, I could respond to one of the questions from one of the general questions about would there be a different flavor from the plant material instead of the oil? And very definitely there is. The oil is going to be a really great solvent for the fat-soluble flavor compounds that have a certain character. The water is really a good solvent that goes with the protein, you know, to carry along water-soluble materials. That's short chain, harsh, very characteristic material. So yeah, there's really a difference between the oil versus the protein in, you know, what components travel, what flavor components travel in each of those two routes.
And the glucosinolates would probably be water soluble.
The products of that would tend to be water soluble, yeah.
Jerry Cohen asked what the profile with essential amino acids was.
I was just typing for Camelina. From my understanding, it's about 40% essential amino acid, and the studies I've referred to, I think it was slightly lower than canola. With canola had about 42% and soy about 49%. Yeah, I'm not sure about Pennycress.
I was gonna say it's very similar between.
Very similar, yeah.
Yeah.
Yeah, you compare the two different methods to extract protein. What is the throughput? For example, as a breeder, I want to compare 300 genotypes. Will that doable? Well, I know this is extract protein from seed. I wonder the throughput for the seeds, and also throughput, like we have alfalfa dry matter, alfalfa. If you can do extract protein from the dry matter, then what is the throughput for the seed and also for the, well, I don't know whether you have that data for the dry matter alfalfa, but what is the throughput of your extract the protein from the seeds right now.
I don't know if Vaidehi wanted to chime in on this. So when we get the seeds, they're whatever the protein composition of the seed is, we typically increase that a little bit. So for Pennycress, we had 26% protein. And then when we defatted, we had the defatted meal that was about 33% protein. And then going from there, we were getting, for that optimized salt extracted protein, let me pull that up. We were getting only the, sorry about this. I mean, roughly 50% of that. So as you're going back through it, I think I calculated it once. Correct me if I'm wrong. I think it's about 16% from the seed.
I think it's similar for Camelina too. At least the protein contents were. So yeah, I would get.
Oh, I may misspoke my question. My question is, what is the through how many samples you can process, like a day or a week?
Whether you want me to answer it, like.
Oh, I want to know. Yeah, the reason I want to know whether I can have like 400 genotype can go there to collaborate for proposal or something like that.
I mean, I can answer part of it, and where they can kind of follow up. So definitely we are using NIR instrument to kind of get the protein content, and that can be done efficiently for both of these winter oil seeds. You can scan each sample in 30 seconds and get protein content and oil content and a little bit of fatty acid composition. But then what Vaidehi did with the 40 lines, eventually we want to be able to get to a point where we can develop an equation where we can kind of estimate the amount of cruciferin or napins in a particular given germplasm, whether it's coming from the mutant population or natural germplasm. So that's where like the preliminary work done by Vaidehi is just see if we can capture that information on gel, and then eventually start building equations that would help us kind of determine those level of napins or cruciferins in intact seeds, so that we could do our selections efficiently.
Yeah, thank you. Yeah, thank you.
And just to add, the 40 lines that I screened, I think I took around, or 18 samples in a day was a good number to be able to run simultaneously gels. But again, with more number of units or just resources available in the lab, I think that number could go up.
Great.
Then the question comes back, how much money do you have?
Well, I will ask money from you, so you will help me to answer that question.
So it's going to be pretty light.
Well, Debbie is here. She will tell me too.
Well, are there any more comments, questions for the team? Anything that anyone wants to bring up? Good conversation and exciting set of presentations, and I think it's going to really set the framework for a lot of interesting research and product outcomes for the future. So for me, it's been going back to the origination of some of this work to get to this point. For me personally, it's really very, very exciting and gratifying, and I hope it's the same for the rest of you as well.
Yeah.
So.
Yep, it is.
So if we don't have any other questions, comments, we'll close up for today. And again, a special thank you to all of the presenters for your very fine work and very fine presentation. So wish you a good day, stay healthy and safe.
You too. Bye-bye.
Thank you, everybody.
All right, bye-bye.
Bye.
Thanks, bye.